Hello everyone and Assalamualaikum. The topic for this video is urine concentrating mechanisms and micturition. By the end of this lecture, you should be able to describe urine concentrating mechanisms, which includes countercurrent multiplication, urea recycling, and vasa recta exchanger mechanism. The second learning outcome, you should be able to describe micturition reflex. Now let's start with urine concentrating mechanism. Urine osmolarity depends on the water volume or ECF osmolarity. In the event of excess water in the body and body fluid osmolarity is reduced, the kidney can excrete urine with an osmolarity as low as 50 milliosmol per liter, which is about 1/6 of normal ECF osmolarity. Normal ECF osmolarity is about 300 milliosmol per liter. Conversely, when there is a deficit of water and ECF osmolarity is high, kidney can excrete urine with an osmolarity of about 1,200 to 1,400 milliosmol per liter. There are two basic requirements in order to produce concentrated urine. These mechanisms are controlled secretion of ADH and high osmolarity of the renal medullary interstitium. As we have learned in previous lecture, ADH regulates the permeability of the distal tubule and collecting duct to water, meaning in the presence of ADH, these tubule will become permeable to water, hence will allow water reabsorption. Water reabsorption hence will allow the production of concentrated urine. The second requirement for forming concentrated urine is the high osmolarity of the renal medullary interstitium. The high osmolarity in the medullary interstitium may provide the osmotic gradient that is necessary for water reabsorption to occur in the presence of high level of ADH. Notice that from the cortex to the papilla, there is osmotic gradient with higher osmolarity towards the papilla. The osmolarity in the cortex is similar to the normal ECF osmolarity, which is 300 milliosmol per liter, and the osmolarity is increasing until it reaches 1,200 milliosmol per liter at the papilla. There are two mechanisms that are responsible to produce this osmotic gradient in the medullary interstitium. These two mechanisms are countercurrent multiplication and urea recycling process. Countercurrent multiplication is a function of the loop of Henle that deposits sodium chloride in the inner medullary region of the kidney, whereas urea recycling is a function of the inner medullary collecting duct that deposit urea. We will look into each of these mechanisms later in this video. First, let us look at the factors that help to contribute to the buildup of solute concentration into the renal medulla. This solute buildup is the factor that causes the osmotic gradient in the medullary interstitium. One of the factors is the active transport of sodium and co-transport of potassium, chloride, and other ions out of the thick ascending limb of loop of Henle into the medullary interstitium. Remember that the thick ascending limb contains a lot of carrier proteins that help solute reabsorption from the lumen into the interstitium. The second factor is the high permeability of the thin descending limb of loop of Henle to water. When water is reabsorbed into the interstitium, it will attract solutes to move along from the lumen into the interstitium. Another factor is the facilitated diffusion of large amounts of urea from the inner medullary collecting ducts into the medullary interstitium. This urea will increase the osmotic gradients in the renal medulla. Countercurrent multiplication is a system where inflow runs in parallel to and in close proximity with the outflow. It is an active process that helps to create osmotic gradient in the medullary interstitium. There are two basic processes in countercurrent multiplication, which are single effect and flow of tubular fluid. First, let us look at the single effect. The initial osmolarity in the tubule and interstitium is similar as ECF osmolarity, which is about 300 milliosmol per liter. This is the medullary interstitium and loop of Henle. So the initial osmolarity is 300 milliosmol per liter. In the thick ascending limb, Sodium chloride is reabsorbed via NKCC2 co-transporter. So sodium chloride is actively transported from the lumen to the interstitial fluid. The thick ascending limb of Henle is impermeable to water, so water is not reabsorbed into the interstitium. Therefore, the tubular fluid in the thick ascending limb becomes hypotonic to 200 milliosmol per liter, whereas the osmolarity of the interstitium increases to 400 milliosmol per liter. The trapping of sodium in the medullary interstitium leads to generation of osmotic gradient in the medulla. On the other hand, the descending limb is permeable to water. Because of higher osmolarity in the interstitium, water will flow out of the descending limb into the interstitium. The osmolarity in the tubular will increase to about 400 milliosmol per liter because of this water reabsorption. The water reabsorption process will stop when the osmolarity in the tubule is similar to the osmolarity in the interstitium. So this is single effect. Following the single effect is flow of tubular fluid. Tubular fluid flows continuously through the nephron, meaning new filtrates from glomerular filtration will enter the loop of Henle starting from the descending limb. So this is the initial osmolarity after the single effect. In the thick ascending limb, the osmolarity is 200 milliosmol per liter because of pumping out of the solutes into the interstitium. The osmolarity in the interstitium increased to 400 because of the solutes, whereas in the descending limb, the osmolarity is 400 because of water reabsorption from the lumen into the interstitium. In flow of tubular fluid, new fluid that has osmolarity of 300 milliosmol per liter will enter the descending limb. So this will cause the high osmolarity fluid in the descending limb to be pushed down towards the bend of loop of Henle and into the ascending limb. This will cause the fluid that was in the ascending limb to leave and enter the distal tubule. The two basic steps, which are single effect and flow of tubular fluid, are repeated until the medullary interstitial gradient is established. This is the initial osmolarity of 300, the first single effect, followed by the flow of tubular fluid. The single effect will repeat again where the gradient is re-established at 200 milliosmol at each horizontal level. Once again, the flow of tubular fluid will take place. The 200 milliosmotic gradient at each horizontal level is established once again. The final vertical osmotic gradient is established when it reaches about 1200 milliosmol at the bend of loop of Henle. This osmotic gradient is maintained by the ongoing countercurrent multiplication of the long loop of Henle, which is the loop of Henle of the juxtamedullary nephron that is located in the medulla. The size of medullary interstitial gradient depends on the length of loop of Henle. In human, osmolarity of medullary interstitial fluid at the bend of loop of Henle is 1200 milliosmol per liter. Urea recycling is the other mechanism that contributes to hyperosmotic medullary interstitium and production of concentrated urine. So this is the loop of Henle, distal tubule and collecting duct. Collecting duct plunges from the cortex into the outer medulla and renal medulla. Notice the line here. So this is the cortical collecting duct, outer medullary collecting duct and inner medullary collecting duct. The unique function of ADH, it increases permeability of the cortical and outer medullary collecting duct to water, but not to urea. So therefore, urea concentration is high in the tubular fluid. However, ADH increased permeability of the inner medullary collecting duct to both urea and water. So here, urea diffuse out of the tubule into the interstitium. This diffusion of urea is facilitated by specific urea transporters, which is UTA1, that is activated by ADH. Because urea concentration is high in the interstitium, it will diffuse into loop of Henle, both descending and ascending limb. This urea will then travel to the distal tubule and collecting duct. And they will again go through the same process. At the inner medullary collecting duct, it will be transported out of the tubule into the interstitium and into the loop of Henle and recirculates many times before it is excreted. So this process is called urea recycling. There are two special features of the renal medullary blood flow that contribute to the maintenance of the osmotic gradient in the medullary interstitium. One of the features is the medullary blood flow is low, which is less than 5% of the total renal blood flow. This low rate of blood flow minimizes solute loss from the medullary interstitium. The faster the blood flow, meaning there will be less time for equilibration. So this will cause solute to leave the interstitium and reduce the interstitium osmolarity. So the low rate of medullary blood flow avoids this from happening. The second feature is the vasa recta as the countercurrent exchanger. Similarly, the importance of vasa recta is to minimize washout of solutes from the medullary interstitium. Countercurrent exchange is a purely passive process that helps to maintain the osmotic gradient. The vasa recta are freely permeable to sodium chloride and water. As blood passes down the descending limb of vasa recta, it picks up sodium chloride and loses water. Solutes will enter the descending limb of vasa recta while water is diffused into the interstitium. So the blood at the bend of the vasa recta has an osmolarity equal to that of the interstitium of the tip of papilla, which is 1200 milliosmol per liter. In the ascending limb of vasa recta, the opposite events will occur. Sodium chloride moves into the interstitium while water enters the vasa recta. So this will cause the concentration in the ascending limb of vasa recta to fall to 300 to 350 milliosmol per liter. This passive exchange of sodium chloride and water in the descending and ascending limb of vasa recta as well as in the interstitium is known as countercurrent exchange. The U-shaped structure of the vessel minimizes solute loss from the interstitium. What this means is, if the vasa recta has only one limb, the blood that will enter the vein will have osmolarity of 1200 milliosmol per liter. So this will disrupt the ECF osmolarity. The U-shaped structure of vasa recta helps to maintain solute loss as sodium chloride will again be reabsorbed at the ascending limb of the vasa recta. So the blood that will enter the vein has an osmolarity of about 325 milliosmol per liter. So we have covered urine concentrating mechanism. Now let us look into micturition process as well as the reflex. Micturition or urination is a process by which urinary bladder is emptied. Physiological capacity of urinary bladder varies with age. At birth, the capacity is about 20 to 50 milliliter. At 1 year old, the capacity is about 200 milliliter, and in adult is about 600 milliliter, although the anatomical capacity is about 1000 milliliter in adults. Cystometogram or CMG is a plot of intravesical pressure against the volume of fluid in the bladder. Cystometogram measures the contractile force of the bladder when voiding. It is indicated in urinary incontinence, difficulty with urination, and neurologic diseases that affect bladder function. There are three components in the cystometogram: 1A, 1B, and 2. 1A is the initial slight increase in pressure with first increments in volume. 1B is a long, nearly flat segment as further increments in the intravesical volume. This nearly flat segment is in accordance with the Laplace law. According to Laplace law, the wall tension of a spherical body, which is the bladder, is dependent on its internal pressure from the wall thickness and radius of the body. So bladder tension increases as it fills, but so does the radius. So the pressure increase is slight until the organ is relatively full. So meaning, even when volume in the bladder keeps on increasing, the pressure increase only slightly because the radius of the bladder is also increased. Components 2 is a sudden sharp rise in pressure as the micturition reflex is triggered. If no micturition occurs, the pressure will keep on increasing. The first urge to void or to urinate will be felt when the volume in the bladder is about 150 ml, whereas when it reaches 400 ml, a marked sense of fullness will be felt, and this may trigger micturition reflex. There are two processes involved during micturition. The first process is the progressive fills of the bladder until the wall tension of the bladder increases above threshold level. The second process is the micturition reflex, whereby the bladder will be emptied. The micturition reflex is an automatic spinal cord reflex. However, it can be inhibited or facilitated by the following centers. Brainstem, mainly in the pons. It has strong facilitative and inhibitory centers. There are also several centers located in the cerebral cortex. It has mainly inhibitory effects, but can also become excitatory. These are the steps in micturition reflex. Increased intravesical pressure will stimulate stretch receptor in detrusor muscle. The detrusor muscle of the bladder has stretch receptor. When the stretch receptor is activated, it will generate action potential or efferent signal via sensory fiber of pelvic nerve to the S2 sacral segment of the spinal cord. Parasympathetic efferents will be sent to the detrusor muscle via motor fibers of pelvic nerve. This efferent signal will excite the detrusor muscle and cause the detrusor muscle to contract. The same efferent signal will also be sent to the internal urethral sphincter and causes this muscle to relax. If there is no voluntary control or inhibition signal by the brain, urine will be automatically voided. Stretch receptor also send efferent signals to the pons. If it is convenient to urinate, pons will return signals to excite the detrusor muscle to contract and to relax both internal and external urethral sphincter, so urine may be voided. However, if it is inconvenient to urinate, pons will send signals to the external urethral sphincter via somatic motor fiber of pudendal nerve to keep the external urethral sphincter contracted, so urine will be retained in the bladder. Brainstem micturition center is present in the pons. It regulates coordinated activation of parasympathetic and alpha motor neurons present in the S2-3-4 segments during micturition at any given volume. Superior frontal gyrus is involved in the social behavior associated with the act of micturition. Bilateral lesion in the superior frontal gyrus will result in loss of control over micturition. Voluntary micturition is a learned ability to control urine from passing down the urethra or to interrupt urine flow once urination has begun. It is done by maintaining contraction or tightening the external urethral sphincter and pelvic diaphragm through pudendal nerve by impulses coming from brains, pons, and cerebral cortex to the spinal cord. These are some abnormalities of micturition. In atonic bladder, sensory nerve fibers from the bladder to the spinal cord are destroyed. So this will result in no micturition reflex, loss of bladder control, and overflow incontinence. In automatic bladder, there is damage to the spinal cord above the sacral region. The sacral cord segments are still intact. However, there is no control from the brain. In this case, typical micturition reflex can still occur, however, they are no longer controlled by the brain. In uninhibited neurogenic bladder, there is damage to brain or spinal cord that control inhibitory signal for micturition. This will cause uncontrolled micturition reflex and frequent urination. So that's all for this topic, urine concentrating mechanism and micturition. If you have any question regarding this topic, please email me at kairuno@usm.my. Thank you.